In this video, we're going to be learning how we can use Backtesting.py to do walk-forward analysis on our trading strategies in Python. Now, walk-forward analysis is a common backtesting methodology used to reduce overfitting when researching and building strategies. It's especially important to do something like this if you're going to be doing lots of parameter optimization, which is in itself prone to overfitting. How it works is that we have a large sample of data. So in this chart here, I've got about 6 months worth of data. So I've got from the 1st of January 2022 all the way to the 1st of July 2022. And this is all minute candle data in my case. Then what I do is I select a 4-week window of time. So that's the blue section here. So this top blue line. I optimize my strategy for that particular time period. So backtesting.py lets us do a grid search to find the optimal parameters, training only on that blue data there. So that top row of blue data. And then we fix the parameters and test the strategy on this orange data, which is going to be our validation set. So that's your standard methodology with your training set and your validation set. But since we've got so much data to play around with here, what we can do is we can roll this forward by the length of our validation data. So we do the same thing again, and we just push this a week forward. So in my case, the training data is 4 weeks, and the validation data is just 1 week. So we move the whole thing forward by a week, we redo the optimization, we retest the validation, and we do this all the way until we run out of data here at the bottom. What this allows us to do is to get a more realistic view of what would actually happen if we optimized our parameters to the last 4 weeks of data and then ran it live. And what we'll also do later on is we'll take all of these validation sets here and join them together so you can see the equity curve for how the strategy performs out of sample. I'll show you that up here. And if we overlay the price here, I'll just add that in. You can see the strategy doesn't actually perform any better than the price when we take into account our walk forward analysis. But it would be very, very easily fooled if we just looked at a single backtest, as I'll show you in a minute. One thing you could also do is you can anchor the base here of this diagram. So I'll just show you, it's easier with a visual representation. And instead of running your training set just on the last 4 weeks, you could run it on all of the data so far. So this might simulate what happens as your model acquires more and more data. How much more or even less accurate does it become? In this video, I'm going to focus on the unanchored approach, but I'll give you a few hints as to how you can very easily include the anchored approach if that's something you were after. So I think that's enough rambling about the methodology that we're going to use in this video. Let's jump into a new Jupyter notebook and we'll code this up from scratch. So I have another tab here and I have gone ahead and imported a few things because you don't want to watch me import a bunch of libraries. Basically, we're using backtesting.py. We're using matplotlib to do our plotting, although other plotting libraries are available. I'm using pickle because we're going to save down our results from the walk forward backtest as it takes a while to compute. Also using pandas and numpy. And you might also want to use this warning suppression here. Currently in backtesting.py, there's a warning about a certain feature being depreciated in the future. And if you use this, you'll stop getting that warning, which is nice. So those are all our libraries. And here's the data that I've got. In my case, I'm just loading here from a CSV. Feel free to get your data from whatever data source you normally use. I'm using data.binance.vision for my data source. This is a super easy way to get crypto price data as CSVs. So you can just go to spot here, monthly, Kleins, which is the candlesticks. Pick your pair that you want. and it gives you just a very nice CSV that you can download here with monthly aggregated data. I picked 1 day here, but you could also pick 1 minute, 30 minutes, etc., etc. So back to the task at hand here, we've got our data, and I'll print that out just to show you the format here, because it's quite important that you have your data in roughly this format. You need the date as a date time index. You need at least the open, high, low, close columns. And if you want to include any other data, you can add that on as an extra series in the data frame and pass that through to backtesting.py if you want. But this is the minimum that you need. You need a date time index, open, high, low, close. Make sure they're spelled with capital letters because that's also important. Okay, so we've got our data. Now let's go ahead and code up our strategy. So the strategy I'm going to be using in this video is a very simple momentum strategy, and we'll use the percentage change in price on 2 different time frames to determine when a trend is starting and when a trend is ending. So this is just an example strategy. I'm going to assume you're at least a little bit familiar with backtesting.py. If you're not, I do have a free course in the description that you can check out and learn a bit more about the fundamentals before we dive into something like this. So let's go ahead and get started. We'll create a new class and it will be called Momentum Strategy, and it'll inherit from strategy. So just a regular old strategy class here. We then need our 2 special functions that every backtesting.py strategy class has. So we've got init, which takes self, and we also have next here. So next, and next also takes self. In init here, we'll want to define our indicators. And in order to define our indicators, we're going to need a function which represents them. If you're using a built-in TA function or other metric that you're pulling in from a separate library, you don't necessarily need this step, but I'll just define a function here and I'll call it momentum. It's going to take in self and the data that we feed it, of course. Data is going to be a pandas data frame here. And so what I can do is I can just simply return data.percentage change over a 7-bar period equals 7. And then I'll convert that to NumPy here to get it as an array. I'll multiply it by 100 and that'll be good. So if there's a 3% change over the last 7 bars, this function will return 3 for that particular bar. Now we've got that, we're ready to go ahead and define our functions here. So I'm going to have 2 separate indicators here. I'm going to have a long and a short momentum. So long is going to be a longer term time frame, so maybe like an hour, 2 hours. And short is going to be a bit shorter, maybe 10, 20 minutes. And that way we can get out of a trade when the momentum's moving against us much quicker than if we were using a longer term time frame here. So we'll do self.percent change long is equal to resample, apply. Let's make it 2 hours here. And we'll apply the self.momentum function that we just created there. And what data we're going to apply that to? Well, we'll apply it to self.data.close.s. So when we run this strategy, we'll be passing in this data here. And from that data, we're going to take the closing values. And we're using resample apply here because we want the 2 hour candles, whereas we're feeding in 1 minute candles. So obviously there needs to be some conversion there. Let's do the same thing and we'll just do a copy of this, but we'll change it to short here. So a shorter time frame. And I'll change that to 30 minutes. So 30t for 30 minutes. This library uses the standard pandas date time offsets, which you can find in the pandas documentation. So we've got our indicators. Now all we need to do is program in our buying logic here. So the buying logic is going to be really, really simple. We're going to go all in on every single trade. So if we have a position, we're not going to take any more trades. And we're just going to look at a combination of the recent momentum in these two indicators to see whether we should enter the trade or not. So change long is equal to self dot percentage change long. We'll take the most recent value. We'll do the same thing for the short over here. And then if we have a position here, so if self dot position, then we want to check whether we should close. And if we don't have a position, we want to check whether we should go long or short. So very simple logic. If we don't have a position, we check our buy conditions. And if we have a position, we close when the momentum runs out. And so we need a threshold of how much momentum is enough momentum to place a trade. So I'm going to define two class variables up here. So we've got our small threshold. That's going to be for the shorter term indicator here, because obviously if you're looking at smaller time frames, on average, there's going to be less volatility. And then we'll have a large threshold. And I'll set that equal to 3, so 3%. So basically, our default strategy here is if there's a 3% move to the upside on the 2-hour time frame and the 30-minute time frame is at least neutral, then we go long. And when the momentum on the small time frame fades, then we get out of the trade. So let's just code that up real quick. If the change in the long momentum here is greater than self.large threshold, and the change in the short-term momentum is greater than self.small threshold, well, then I want you to buy. So self.buy here is just going to go all in, basically. Then we'll program in the logic for placing short trades. So it's just going to be the inverse of this. So I might as well just copy and paste here. So I'll copy this. So if the change in the long momentum is smaller than -1 multiplied by our threshold here, so if the price moves down 3% on the 2-hour time frame and it's less than 0 on the shorter term time frame here, well then let's place a self.sell, and that's just going to place a short order with 100% of our money here. So if we have a position and the position is long, so if self.position.is_long. If we have a long position and the short-term momentum goes underneath this threshold, then we want to immediately get out of that trade. So if the momentum starts to fade, we want to get out. So and change short is less than self.small threshold, self.position.close. Okay, similar sort of logic here for the short trades. So L if self.position.is_short, and the change in the short-term momentum is greater than -1 times the self.small threshold. So that's our entire strategy class here. That's a fully functioning momentum-based strategy, although I can't vouch for its effectiveness, as we'll see later on. Let's give it a run here just to make sure that it's actually functioning. And all we need to do that is to create a backtest object here. So you can do BT is equal to a backtest. Then we feed in our data. So I'm just going to feed in a small amount of my data because I have a lot of it and I don't want to run a 6-month backtest here. So I'll do data.index is less than 2022.02.01. Obviously, you'll want to adjust this for your particular data set. We feed in our strategy class, so momentum strategy is what I named mine. So it's just the name of the strategy up here. I'll run this cell so it actually works. Of course, there's a nice syntax error. Self.position.close here. Let's supply our cash here. So cash, I'm going to set the cash equal to 10 million here. The reason why I'm doing that is because I'm using Bitcoin price data, and backtesting.py doesn't play too well with fractional shares. It just doesn't work. And so if you're trading high value assets, it can be a good idea to increase the cash. Or alternatively, you could divide the price of the asset by, say, 1 million, and then you're trading in micro Bitcoin. Let's also add some commission in here to make it vaguely realistic. So equal to 0.002, so 0.2%. We've got that. Let's do a bt.run and then a bt.plot to plot out our strategy here. Now, the graphing can be a little bit strange on a Jupyter Notebook environment here. Sometimes it works, sometimes it doesn't. You may have to use a different IDE like Visual Studio if the graphs aren't to your taste. Of course, you could always code up your own graphing implementation in something like matplotlib. But this seems to be functioning here. You can see it's placing a number of trades and losing me about 4% over the course of this time period. But that's okay. We know better. We can radically overfit our strategies here using the optimizer. So instead of just using these default thresholds here, we can get the computer to check a variety of different combinations and only spit out the one which gives us the most money at the end. The way we do that is instead of calling bt.run here, we get the bt optimizer. So we'll do bt.optimize. And then we need to provide a range of values for all of the class parameters here. So we've got small and large in my case. You may have more, you may have less. So I'm going to set my small threshold here is equal to numpy.arange from 0 to 1 in steps of 0.1. So that's just going to be 0, 0.1, 0.2, 0.3, etc., etc. And I'm going to turn that into a regular Python list here because otherwise backtesting.py complains. But essentially what this will produce is just a list from 0, 0.1, 0.2, 0.3, etc., all the way up to 1, although I believe not including 1. So let's copy this out again, and we'll do the same for the large threshold here. So the large threshold, except we'll go from 1 to 3 in steps of 0.2. The final thing we need to tell the optimizer is what do we want to optimize for. Now in my case, I'm just going to optimize for most amount of money at the end of the time period. And you do that by providing a maximize argument here. So maximize, well, that's going to be equal to the equity final dollar, like that. I'll show you where you can find all the other options in a second, but we'll just run this for now. Let's see if that works. Seems to be taking its sweet time, so that's usually a sign that the optimizer is running because it's got to run every single combination of these two things. So in our case, that's probably about 200 different backtests it's running there in the background. It looks like it's now moved on to plotting because it's complaining about how many candlesticks we had. And as you can see, this performed very, very marginally better than the previous one that we did there. We have a final equity of 98% rather than, I think, 96 it was before. So Optimizer did something at least. If you want to find out what the values were used in this particular backtest, we can extract the stats here from bt.optimize. If you do stats equals bt.optimize, you'll have to run the whole thing again, unfortunately. But if we just give it a second here, we can now print out these stats. So let's go down to the next cell here. So print out stats that we just gathered. That'll give you all of these different values. So this is where you can pick your new maximize value if you wanted to. So let's say for some reason, instead of maximizing the final equity here, you wanted to maximize your win rate. You could include that as a maximize value. Now, if you want to extract the parameters that were used in this particular strategy, so you'll notice on the graph here, it doesn't really tell us what's happening. If you go down into stats here, you can see we've got this strategy object being hidden inside here. And so we can extract that out if we want. So we do stats._strategy to extract that here. You see we get a momentum strategy object, and we can clearly see the parameter values here, and we can extract them quite easily by doing something like small threshold. We'll be needing this in a later function that we're going to use, so you get 0.8 here. You can also extract your trades here if you want. So this will give you all of your different trades. And you can also get the equity curve, which we'll be using later on again. This would be helpful if you wanted to use a custom plotting library, again, as we will later on. So this is great. We've got a functional strategy here, but we're all here for the walk forward optimization. So let's actually get going on that. And it's surprisingly easy to implement once you've got a working strategy. And after we've built up the surrounding infrastructure here with a few functions, it's essentially just plug and play. You can easily drop new strategies in there, no problem at all. So we'll scroll down here, make a new cell in our walk forward section. So I'll make a function here that calculates all of the separate backtests. If you remember back to our initial diagram here, you can see we've calculated 21 different backtests here. And so what we're basically going to do is a fancy for loop where we just take small sections of the data and backtest on each of those. So coming back here, let's define a function. I'm just going to call it walk forward, nice and simple. And we're going to have quite a few inputs here. So what do we need? Well, we need the strategy that we're going to be forward testing. That's pretty important. Can't do much without that. We need the data. So we're going to have the full data frame of data, our entire region that we want to exhaust. We'll also want to take in some warm-up bars. So if I scroll up to the top here, you might be able to see in this plot, if I click on this, you can see because this is using 2 hour time frames here, at the beginning of the trade window, the indicator isn't fully there. We don't want that to happen, and it's especially important to avoid that in our validation test that we do, because that's using a much shorter range of data, so this period here is going to be much longer. Don't worry, I'll show you how to avoid that in a second, but coming back here, we need a number of warm-up bars, basically. So the number of bars until that indicator starts producing values. That'll obviously be different for everyone. We then need the look-back bars here. So look-back bars. This is going to be the amount of bars for the training set. So in my case, it was 4 weeks. And then, of course, we need the validation bars. So this is how many bars we use in our validation set. We'll use the cache here. So cache, I'll just set that to 10 million by default. We don't really need to provide that every single time. And of course, the commission here, I'll just set that again to 0.002. So we've got all our inputs here. We should be ready to go and actually build out this function. So I'm going to create a list here, and I'm going to call it stats master. So this is going to store the results of every single validation test that we do. So every time we test one of these orange periods here, the stats object that gets created, so this object here, we're going to save that in a list, and we're going to have a list of these objects, which we can then further analyze and plot data about. But these stats objects ultimately contain all the data we care about, and so that's why I'm just going to extract those and return those eventually at the end of this function. So we'll start our fancy for loop here. We'll do for I, so I is just going to be a counter in this case. It's going to be the number of bars. For I in range, we'll start at the look back bars. We'll end at the length of our data frame minus the number of validation bars. So we always want to make sure that every time we do a training backtest that we can do a validation backtest after it. And so we need to make sure that we end at this point. And what's the increment that we're going to move forward by? Well, we move forward by the number of validation bars, right? So again, going back to the diagram, probably getting a bit repetitive, but every single time we do the backtest, we move forward by the amount of bars in our validation set here. So that's all well and good. We've got our nice fancy range function. What we can then do is we can just grab training data and validation data. So sample data is equal to data full, so our full section of data. But then we're going to slice into it with .eloc for integer location. We're going to go from I minus the number of look back bars. So look back bars. So for the very first one, this is going to be from 0, and then it's going to be from the number of validation bars, then from 2 times the number of validation bars, so on and so forth. And we're going to go forward until we get to I here. That's going to be our sample data. Our validation data here, well, it's going to be relatively similar. So data full.eloc, but we essentially want the next 7 days, in our case, after this particular sample data. So we go from where this data ends here. So this ends at I. We go from I to I plus validation bars, which for me is going to be 7 days. Hopefully that makes sense to you. If it doesn't, you can print them out, check that they all line up and that kind of thing. What we can do here to make sure that we have enough warm-up bars is on the validation set, we can minus the amount of warm-up bars here. And we can also do that for the sample data by just adding on here. So add the warm-up bars. And then in here, you just take off the warm-up bars again. In my case, as you saw in the strategy we developed earlier, I'm using the 2-hour time frame and I'm using 7 of those to calculate my momentum. And so therefore, I need to make sure that these different data sets here have at least 14 hours of data that they can pre-compute before the trading period actually begins. So we've got our sample data, we've got our validation data. We're on the home stretch here. All we need to do is to run our optimizer here. So it's going to be BT training here. I'll change this to training data so it's a little bit more obvious which is which. BT training is equal to backtest. So we're just creating a backtest object here. We're just doing a full backtest like we did before up here. So very, very similar to this code here. Except obviously we're going to use a different range of data. We're going to use this validation and training range that we had from before here. So BT underscore training, well, that's going to be equal to backtest. We'll use our training data. We'll use our strategy that we pass in here. So whatever strategy gets passed to this class, or this function rather. Cache, well, that's going to be equal to the cache value, again, provided to the function. And the commission here is just going to be whatever is provided to this function. We'll then do some optimizing here. So I might just go grab that code directly from before. So it's just this bt.optimize code. Rather than typing all out again, I can just copy and paste it down here. And indent this. Stats. Training. So this is the training stats. I'll indent these a bit more so it's clearer. So this is going to produce the optimum combination of parameters for our training set of data here. And to extract them, as I showed you before, fairly easy. So small threshold is equal to stats training. Then we extract the strategy with the underscore strategy. And then you extract the parameter that you want. So small threshold. I'll copy and paste this. And we'll do the same thing with the large threshold here. Large threshold and large threshold. And now that we've got our optimal parameters here, we're now equipped to run the validation backtest and save those stats into this stats master dictionary here. So the validation backtest going to be much like this one here. So I'm going to steal this if I can copy and paste it. So it's going to be BT validation, if I can spell validation, is equal to backtest. This is going to be the validation data. Same strategy, same cache, same commission. You'll want to make sure these are the same, otherwise things might get a bit messed up. Instead of doing bt.optimize, we're going to do bt.run since we know the combination of optimal parameters. So we'll just do stats validation is equal to bt validation here dot run. Then we provide our optimal parameters. So small threshold is equal to small threshold, large threshold is equal to large threshold. So that looks good to me. We've run our new optimal set here on the validation data. And we can now just append the validation stats here to our stats master. So stats master.append stats validation. So that will add that to that list. And then outside of this for loop, once we've ran the walk forward analysis here, we'll return the stats master list. So hopefully that should be our entire walk forward function done. This is really quite reusable for other different strategies. Basically, all you'd have to do is change the parameters that you're using here, perhaps. And of course, the parameters that you're extracting from your finished backtest here. But I'm sure you could automate this even further to the point where it's simply just plug and play any valid backtesting.py strategy into here. Let's give this a run, check no syntax errors. That's a good sign. And we'll give this a whirl, just see how it works, make sure everything's actually functional here. So we'll set our number of lookback bars here. So lookback bars. Now in my case, I'm using 1 minute candles and I want 4 weeks of data, so 28 days. So 28 multiplied by 1440, which is the number of minutes in a day. Do alter this for whatever time frame of data you're using, or make some function that does it for you. I want the validation bars here, so I'm going to use 1 week of data. This is not fixed. You don't have to use 28 days and 7 days. You could use 25 days and 10 days. You could use 30 days and 10 days. There's no fixed rule about that. But generally, when I've seen other people do walk forward analysis, they use maybe 75%, 25%. And then we need the number of warm-up bars. My strategy needs 14 hours of warm-up bars. If you want to know how many you need, all you have to do is go back to your strategy here at the top. Zoom right in on this moment. So whenever this is. So this is the first candle here where data starts being produced. You can zoom right into it thanks to the nice plotting interface here. And you can see that the first bar that actually has data here is 5 minutes past 4 p.m. And the data starts at 12 a.m. that day, so it needed 14 hours. Or rather 16 hours here of training data until it produces its first bar. You want to make sure that you don't include too much warm-up data, so you want to get it just to this level here, because otherwise you'll start including data in your validation set that should actually be in your sample. You'll start trading during your sample period, which is a big no-no. So I'll show you how to plot this later on so that you can narrow this down if you're having trouble with that. But let's continue here with our walk forward. So we've got the lookback bars, that needs to be 16. We've got the validation bars, and we've got the warm-up bars. Now all we need to do is run our walk forward function. So I'm going to say stats is equal to walk forward. We'll pass in our momentum strategy. We'll pass in our full data frame of data. And then we need to pass in our lookback bars, our validation bars, and our warm-up bars. I'll just give the formatting some space here. So the lookback bars is equal to lookback bars, validation bars is equal to validation bars, and the warm-up bars is equal to the warm-up bars. Okay, that should be everything that we need here that doesn't use a default. What I'm going to do is I'm just going to put a break in here. And so this means after the first iteration of the loop, it will break and therefore return. It just means that we're not waiting here a really long time for this to produce its results while we're just testing here. So I'll run this. Seems to have hit some sort of error. Commission is not defined. I probably smelt commission wrong here. Yep. Let's run this again. Run this again. Seems to be working this time, so that's an improvement. Okay, so I'll open up a new cell here, and I'll just print out the stats. See how that's looking. So we have 7 days and 16 hours, so our warm-up time was 16 hours, as we discussed previously. We don't need to pay too much attention to these values. One thing that might be worth doing is checking the strategy object here. So I'll get stats._strategy. The reason I'm doing this is just to get the values here that were used in the optimizer to make sure the optimizer is actually working. It's giving me an error here, but that's just because the stats here is actually a list, if you remember. So we just need to index into the first entry of that. You can see it's using 0.8 and 2.8, which are not the default values, which implies that the optimizer is working. And so as far as the walk forward section of this video goes, I think we're basically done here. You can remove this break here, and it will just run this on a loop, and you can perform your analysis. And so as far as a bare bones strategy here for how to do a walk forward analysis, that's pretty much all you need. You can just get rid of the break statement that we put here, get rid of that, and it'll loop through all of your data and print out all of these nice stats objects here, which you can then print out in a big list to figure out what's going on inside each of these validation sections here. And that might well be enough for some of you. In the rest of the video, I'm going to be going into a deeper analysis of these different validation sections here to make sure that we've done the test correctly. And we'll be producing a number of charts and graphs like this one here, and of course our equity curve. And I'll also show you how to replot the backtest for a given stats object. So you can use this stats object that you get from our walk forward analysis, and you can produce a plot that looks like this from that stats object. So I'll show you how to do that as well. Let's start by plotting out the results of our particular backtest. That can be extremely useful here, as it'll help us find if we've made any mistakes in this walk forward function here. It'll be relatively obvious once we plot it out, and just to make sure that our strategy is behaving sensibly here. So I'll get rid of that, and we'll plot a particular result here. Now the way I'm going to do that is just using a regular Python function here. So let's make a function, and we'll call it plot stats. It's going to take in two different things. It's going to take in the data. So this is just going to be our full data frame. So I'll call it data full, make it more obvious what it is. And it's also going to take in the stats object. So again, the regular stats object we've been working with this whole video. So from our walk forward, you get a full list of them. Pick one of them, pass it to this function, and it will plot it. At least that's the idea. So the way we do this actually is we create another backtest object here. So BT is equal to backtest. We'll use our data. We'll use our momentum strategy. So basically just make sure these are exactly the same as the ones you used in your walk forward analysis. So cash, that's going to be equal to 10 million again. Make sure that's the same. And make sure your commission is also the same. So we'll create this new backtest object, and then you can just call bt.plot, but instead of just allowing it to plot whatever it wants, we can pass in the results is equal to stats. And so it'll behave as if it actually simulated that set of results, except obviously we haven't actually done any computation here. So if I run that, and then I create a new cell, let's run plot stats here, so plot underscore stats with our full data set, and we'll index into our stats list here. So remember, stats is a list. We'll index into that at the 0th element. Now we do, of course, get an error here. And the reason for this error is that the range of data that we're using inside our data full here is different from the range of data that was used to actually create this, right? So this is only a validation backtest, so it's only 1 week of data, whereas the data full here is like 6 months worth of 1 minute data. Easy way to fix that is you can extract the equity curve here. So equity curve is equal to stats dot equity curve. So that'll grab the whole equity curve for this particular backtest. I showed that before when we looked at the stats object. And then I can just build a data frame of aligned data here by doing data.reindex equity curve.index. So all I'm doing here is I'm I'm taking the range of data that was used to produce this equity curve, so i.e. the data that was used to produce this stats object, and I'm re-indexing our original data frame here, so our full data frame, with that particular index. It basically just means that we cut out all of the data that wasn't used in this particular backtest. And now I can pass in align data here and run this twice and it should work. So it's complaining that we've got too many candlesticks, which is a good sign. It means it's actually doing something. And there we go. It's producing our plot here exactly as we wanted. And we can also go in here and check that our warm-up period is correct. So we can look at the exact time here at which this gets started. So this seems to be getting started at 4 p.m., which is not what we want. So remember, our validation set here should start at midnight on the 29th here, but we should have 16 hours before this for the warm-up bars to be calculated here. So something's gone wrong. Let's have a look and see what that might be. The only thing I can think of here is that something's gone wrong in our warm-up. That is the correct amount of bars, so let's go check up here, see if something's gone wrong. It looks correct to me, so I'll run this again and just check. So we'll run this again. We'll run our walk forward here. I guess what we might want to do here is we can print out our validation data. So print validation data. And we can also print out our training data here. So print training data. So I'll print those two things out, and then that should give us a clue as to something's gone wrong. So here's our training data. And looking at this data again, now that I've got this, I can see that our walk forward optimization is actually working properly here. So if you think about what's going on here, we've got essentially 28 days, so 4 weeks and 16 hours of data. That's how this is functioning. The first 16 hours are just to calculate our indicators. And so this 28 days is from the 1st of January at 4 p.m. to the 29th of January at 4 p.m. or 3:59. That's the 28-day period that we've chosen here. And so the validation test here is also going to be starting at 4 p.m. because we want it to start straight after this training set finishes. So we want the validation to start at 4 p.m. on the 29th here. And we want it to end exactly 4 days later on the 5th at 4 p.m. This first 16 hours are purely to calculate our indicators. And because our indicators aren't calculated, no trades will be taken, which means that this data here, which is part of our training set, won't actually be used in our validation. So we kind of went around in a big circle there and discovered that we were actually doing the right thing all along, but better to do that than find you've got some massive hidden error somewhere. So we're happy with that. Let's continue. And yes, as I said before, I'm happy that this starts at 4 p.m. Given the data that we already have, that's when the backtest should officially begin, because it's not including any of our training set data. So that's good. I'm now convinced that my walk forward optimization is working somewhat effectively here. So what I'm going to do is I'm going to go ahead and run this without the break. So I'm going to calculate all of the different backtests here. So I'm going to calculate this entire waterfall of different backtests. There's 21 of them. It's going to take a little while, so I'll let that run here and I'll speed through. So run this and run this. One thing that's nice about Backtesting.py is that at least on Linux and I believe Mac, it should make use of pretty much all of your processing power. I think this might be slightly bugged on Windows right now, but you can check for yourself. Just look in your task manager. You can see that basically 100% of my CPU is being used here to do all these various optimizations. And it's honestly not that heavy on RAM here, which is very nice. So I'll let this run and we can compare results at the end. So there we go. It looks like the calculations have finally finished here. Let's open up a new cell and let's just get the length of stats here. If everything's worked correctly, there should be 20 to 21. There we go, 21 different stats objects. Let's print out, I don't know, the last one, so -1, and we should get a regular stats object. Great. 7 days and 16 hours. The 16 hours is our warm-up period. Looks like everything's going great. So now that we've got this list of stats objects here, you can start to do some analysis on your different sets of validation data. So, for example, one thing we could do here is we can compare the equity here with the buy and hold return, and we can see how well or poorly our strategy does compared to holding. We can look at things like the mean and the median of the returns, that kind of thing. Easiest way to do that is we can just go in here and we can get the strategy returns. Well, that's just going to be X, then the return here, for X in stats. So just a simple list comprehension there. You can do the same thing here to just get the buy and hold return. So this is going to be hold, let's call it hold returns here, hold returns. I think I've put myself in a different mode here. So returns like that is equal to our list comprehension. That looks like it's working. And we'll just need to copy buy and hold return from here. Perfect. So now what you can do is import statistics. I must have done something wrong here. Yes, I forgot to include a closing bracket. The formatting tips me off there. And we can do things like, we can print statistics.mean of the hold returns. And we can do the same thing for the strategy returns. Many, many hours of fun can be had examining these results. So I've spelled statistics wrong. And there we go. So you can see that the mean for the strategy returns was less bad than the mean for the buy and hold returns, but honestly, neither of them ideal, and so you probably wouldn't run this strategy in reality. Whereas you may have been deceived if you just ran a single backtest, and especially if you didn't separate out your validation and training data as we did here. So a median, strategy returns. You can see the median is very, very slightly better here than buy and hold. But I think what's more effective than just these single little stats here is looking at the full equity curve on this entire waterfall. So imagine you joined each one of these orange bits together and you ran that as the strategy. What would that equity curve look like? Well, thanks to the magic of Python, we can calculate that just fine. So this is going to be a little bit of a lengthy function, but hopefully we can get through it intact. So define a function. I'm just going to call it plot full equity curve. Very imaginative there. We need to provide some data, of course. This is going to be our price data. We'll also need the stats list. So that's the thing that we just spent like half an hour computing for, that big long list of stats objects. We'll need to give it our warm-up bars. We'll need to give it our look back bars. And that should be good for now. So let's go ahead and get started. So the first thing that I'm going to do is I'm going to extract all the individual equity curves from this stats list here. So we'll do equity curves is equal to X. Let's take the equity curve dot eloc warm up bars. We don't want to include that in our equity curve because then there'll be overlapping between the different tests here. So again, if we think about this diagram, in reality, we've got about 16 hours of extra data here, so you add a little bit extra on, but no trades actually take place during that time because our indicators aren't calculated. So we can safely ignore that when we're drawing out our equity curve here. So from warm-up bars till the end, that's fine. And then 4x in stats list. Okay, so we've got all our individual equity curves. That's great. For now, I'm just going to join them in one big pandas series here, and it won't really make much sense, but don't worry about it too much for now. So combined is equal to pd.concat, and we'll just straight up provide the equity curves in here, and that should work. So if I print combined, you'll see what happens if I run this in a new cell. So plot full equity curve. I'll provide the data, the stats list, the warm up bars is equal to warm up bars, and the look back bars is equal to the look back bars. Let's run this, just make sure it's vaguely working. So you can see here what happens is it plots out the full data frame of equity curves in here. Now, if you were to plot this out, this is not going to really make a lot of sense because it'll keep getting reset to 1 each time we hit a new validation set. So again, I'll go back to the diagram, and basically it'll start at 1 here, and then let's say it gets to 3%. Currently what happens is it starts at 1 again, and then let's say it gets to minus 2%, and it starts at 1 again. So we need some way to join all these together and make them make sense. I'll do that after we've plotted everything out so you can see what's happening. The next step that we need to do is we need to align this price data here. So we've got some price data, but that's not going to be aligned to all of these orange sections here. So we're joining all the orange sections together, and we want the slice of price data that represents that section. The way we do that is I'll make an aligned data frame here. I'll call it aligned price data. And that's going to be equal to data before this date here. So this is the last date in all of our validation sets. We want to make sure that we cut that out. So data.index, so the time is less than or equal to combined.index or rather slice -1. So we get this last entry here, and we want to make sure that none of the price data goes past that point because it'll look a bit weird on our graph. We also want to cut off some data from the beginning, so .eloc, and that's going to be look back bars plus warm up bars. The reason for this is if you go all the way back up to our walk forward function, feels like a long time ago now, you can see we start on that value. That's the first value of I, and the equity curve for the validation data here starts on the first value of I. So that's why that's happening. Okay, so we're feeling pretty good here. I'm just going to plot some stuff out. So this is using matplotlib, which I imported right at the very beginning. Other plotting libraries are available. Let's do fig x1 is equal to plt.subplots. We'll do x2 is equal to x1.twinx. So that's going to produce a secondary y-axis for us here. We can draw our equity line here with x1.plot. Then on the x-axis is going to be combined.index. So we're basically just plotting this against this. The y-axis is going to be combined.equity. And we should be able to leave that for now. On x2, we're going to plot the price. So x2.plot is going to be aligned price data.index. And then aligned price data.close. And then at the end, if we do a plt.show, this should look relatively reasonable. We'll have to do some cleaning up. Okay, I forgot a slice there, so it just took a particular value. That was confusing me for a while there. Let's try this again. So we've got our equity versus our Bitcoin price data. It's all a little bit crazy at the minute. Let's add some colors in there. Maybe that'll clear things up a little bit. So color is equal to orange. That's a little bit nicer. Now, the main job here that we need to do is we need to connect all these equity curves. So they're just kind of disjoint equity curves that get restart at 1 every time. The way you do that is, instead of just joining them together here, what we can do is we'll go through each of them and adjust the starting equity of each of these backtests to be the finishing equity of the last backtest. So what that looks like is, instead of initializing this combined value here with the full concatenated equity curves, we can just make this a blank series here. So pd.series. And then for every curve in equity curves, well, what do I want to do? Well, if the length of combined is equal to 0, so i.e. if there's nothing in our current combined equity curve, well, then just set the value of combined equal to the curve. We'll take the equity column, And we'll also divide it by the amount of cash we have. So 1e to the 7, 10 to the power 7, 10 million. Basically, just divide by the amount of cash that you have such that this is 1. The starting value should be 1. And then if we do have some elements in combine, so else, then what I actually want to do is I want to take the last value in combined, multiply the new curve by that value, and then add it on to the data frame. You might need to print some stuff out to get an idea of what's happening, but maybe it'll make sense when I write the code here. So combined is equal to pd.concat. We'll do combined, and then the second thing, so we're going to join combined with something else. The second thing is going to be, so our new equity curve here. We'll take the equity column, so we just want the equity column, divide it by 1e to the 7, as we did before. So the starting value is going to be 1. They're all going to be normalized to 1. Multiply that by combined.eloc minus 1. So basically, what this code does is it should join all the equity curves together, so they look less disjoint. We've got a nice error here. Of course, this no longer has the equity attribute, so we don't need that. This is just a regular pandas series now. It's no longer a data frame. And there we go. You can see our equity curve has all joined nicely together. What you can also see is that our strategy follows pretty much to a T the price of Bitcoin here, perhaps with a little bit of a delay, but it really doesn't do that well when compared to just buying and holding. So that's us done here for the equity curve. You could add things in, like you could change the style if you want. So plt.style.use 538. So you can add different matplotlib style sheets in if you want, just to make it look a bit different. That looks rather horrific currently, but I'm sure you could fix it up. Overall, I think I've given you everything you need to plot out the equity curve here. So I'm going to move on to our final graph here, which is just this one from the beginning, just so you can make some nice plots. It's a relatively simple diagram to draw out. I'll again create another function here, so I'll call it plot flow graph. So it plots the flow of the walk forward optimization here. We'll take the data, again, our price data frame, and we basically just need the look back bars and the validation bars. So I'm just going to copy those. In fact, I won't. So look back bars, and we also need the validation bars. And that should be good for now. We're not actually going to use the same object that we created in our walk forward optimization. We're not actually using the same object. We're just going to recreate the object by using the same range of data that we did before. The first thing I'm going to do is I'm going to go ahead and do that. I'm going to go grab from our walk forward function this range here. So basically, I want a list of all these values of I. So what are the offsets at which each new set of training data begins? So I can do ranges is equal to list, and then just pass in this range. That'll produce a nice list for us. And then we can do for I in range len ranges. So I is just going to now be a number between 0 and 20, I believe. I'm doing that so that we can use I as the value on the y-axis for the positioning of the training data here. So you can see they're all on separate rows. So we're basically going to decrement I by 1 each time, and that's how you create this staircase effect. So for I in range len ranges, that's great. Let's grab our sample data here. So in fact, we can probably just go back to this walk forward function, and we can just grab these two, come down here and paste them. That'll just make sure that we're actually getting the exact same values as we used before. This plot's really just for show. It's not actually doing anything, but we still want to be accurate here. And everywhere you see I, just replace that with ranges I. Remember, I is just some integer now. We actually need to index into this ranges list in order to get the offset. So I'll go here, 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 and here. I think that should be everything. So we've got our training and validation set for that particular offset. We don't really need to show the warm-up bars in this plot, so I'm going to remove that, as no trades are actually placed in that location, so this plot only shows places where we're placing trades. So we've got that. All we need now is a very simple plt.fill_between. This one's going to be for our training data. So it's going to be training data.index. That's just going to be the dates. And then we're going to provide two values for it to fill between. So basically, this y value and this y value here, it's going to fill those with solid colors. So you want the top and the bottom. The way I'm going to do that is we can take the length of the ranges variable here. So this is the total amount of offsets, the total amount of backtests that we actually did. We can minus I from that because we want this flowchart to go downhill as we progress. And then we're going to minus 0.5 because this is the bottom of the bar. And then we're going to add 0.5 to the top of the bar. So the bar is overall 1 thick. So this is just a regular old number here inside this list. What I'm then going to do is I'm going to multiply that by the amount of elements in our sample data.index. So take this regular number and plot it out this many times, and you'll get the result you're after. I'll copy and paste this value here onto the next line, and we'll just add 0.5. So that's going to be the top bar, and then we just need to provide a color. So color is equal to blue. Okay, and then I'll do the exact same thing over here. So we'll go fill between, except we'll use the validation data here. So validation data, I'll copy that for all of these, and we'll use orange instead. Finally, after the end of this for loop, you want to do a plt.show. And then if I make a new cell and plot all this out, we should be looking good. So plot flow graph, I think is what I call it. Yep. Let's provide our data. Look back bars is equal to look back bars, warm up, or is it validation? Validation bars. Validation bars is equal to validation bars. Okay, let's run both of these. Data full is not defined, of course, because it's just data. I used that a few times apparently. Sample data is not defined because I called it validation data. Or rather, I called it training data. And there we go. We've got our nice waterfall plot here showing all of the different backtests that we did. You can stretch it out like I did previously if you do fig x is equal to plt.subplots, and you do fig.set fig width to 12. That will make it a bit wider and might look a little bit prettier. So I hope you enjoyed that journey into walk forward analysis with backtesting.py in Python. If you like the content, make sure to subscribe, and I'll see you in the next video.